Okay, guys, so today I'm going to do a quick solution of the exam. I have almost all of them graded except for 3 or 4 of them. So I might give you back the exam to everyone except for the 3 or 4, okay? And I'll give it to you next time, unless we don't have time today. So again, I'm going to do a quick solution. So what was the goal of the first problem? So let me just redo the figure here very quick. So let's see, 1, 2, 3, 5, 6, 7, 8. We have here a 4,100 pounds. 2,800 pounds and 1,500 pounds, and the distances were, let's see, 15, 11, 20, and 9. Oops, okay, doesn't matter. So what is the goal of this problem? Okay, something we learned at the beginning on doing the basic design is that the basic design is that each one of these members, each one of these flanges is what type of member? So one force member, meaning what? That each one of them can carry just a load in one direction. Okay, so that's the whole idea about the design. So for example, this one here, this load over here, like the 4,100 would be carried by which member? The 572, no? Okay, but probably here the one logical to start with was what? To start with the member 7,8, that one should carry the 2,800. Okay, so I don't remember exactly how this was, but I think over here this was Q1. So this is the sign convention I've been using. If you decided to change it, that was fine, as long as you're consistent. This one here will be Q3. And this one here will be Q2. Okay, so basically what I'm looking over here for is that you understand the one force member. Okay, so I think the logical stuff to do first is to take flange, or let's say stiffener 7,8. Okay, 7,8. And now what do you need to show is that on this side is going to have Q3. On this side, Q1. And this will be 2,800. Okay, and that distance is how much? Is 20 inches. So here doing summation of forces, so you can do summation of forces equal to 0. You can do summation of forces external equals summation of forces internal, okay? Either one would work. I actually need to do more this one because it shows me that the internal reactions need to counter-react the internal, no? Okay, but I mean, if you do this one, you get also the answer. So for this one, for example, you will get then 2,800 needs to be carried by what? 20 Q1 minus 20 Q3. Okay, and this will give you a first equation that will be what? Q1 minus Q3. So this will be 1,400, 140. Okay, let's say that could be your first equation. Next, which member can we take that relates also Q1 and Q3? The 681. So we take the 681, come here. 681. And this time what do we know is the 1500 load over here. And let's see, this is 11 inches, 11 inches and 15 inches. But most important is to know that here we're gonna have Q3 going up, and here we're gonna have Q1 going up. So if I do the same thing here, summation of external, summation of internal, what do you get? 11 Q3 plus 15 Q1 should be equal to what? Minus 1500. And this should be equation 2. So now what do you have? Two equations that relate Q1 and Q3, no? So two equations to unknown. So let's say solving Q1 minus Q3 equal to 140 and 11 Q3 plus 15 Q1 equal to minus 1500. We get over here Q1 equal to 1.538. Q3 equal to negative 138.46. Okay, 1.5 really, but if you round it off, it doesn't matter at all. Okay. And this should be, I didn't count anything off for not having the correct units, LB per inch. Okay, so now finally, we need to find Q2. So what is the stiffener we can use now? 572. Okay. So using Q3, Q1. Oops, no, I did opposite. Sorry, guys, this should be Q3 on this side, Q1 on this side, and this one should be all. Sorry for my figure. All this should be Q2. Okay, let me redo a figure. I always say a good figure is important, and this is not a good figure. So let's do a good figure. So this, and this. So we're gonna have on this side Q2, Q3, Q1. And here we have the 4100. Okay, and the distances here were 11 and 15. So again, if we do summation of forces, external summation of forces, then what do we get? We're gonna get 4100 will be equal to what? 26.2 minus 11 Q3 minus 15 Q1. So if we solve for Q2, This should be equal to what? 4100 plus 11 Q3 plus 15 Q1 divided by 26. And I think this one was given 100. Pound per inch. I mean, any questions so far? I agree that the goal here for me was to make sure that you understood that each member of flange or stiffener will carry just one load in one direction. Okay. Then at the end, I think I asked you to find the distribution. Stiffener. It was 572. Yes, 572. I have it right here. Okay, so the 572 is the one we just did over here. So some people were pretty smart because what should be the load at 5? It should be 4100, no? But what should be the load at 2? 0. So some people started from this end, which I think is smarter. Personally, I started from the top. But let's see if I start from the top and I make a cut over here, then what should I get? This. Then what do you get? You get here the 4100. You get over here the Q3. You get over here the Q2. This is your S. And here you say this would be Q, whatever, it would be 57. Okay, so this will give you what? $4,100 will be equal to what? Q2 minus Q3 times S. Let's say if I do it this way, minus P57. So then what do you get? P57 would be equal to, let's say, Q2 minus Q3S minus 4,100. Okay, so that shows you that at S, what should be the load? 4,100, no? Yeah, at S equals 0. Okay, now if you want to have the load on this section, what do you need to do? Make this one a bit longer, but we follow exactly the same procedure. 4,100. This is 5, 7. So this will be now T72. Again, we can have here the S. Yeah, okay. And here you're gonna have what? Q3, Q1, Q2. If you do summation of forces, external of a summation of forces internal, what are you gonna get? 4,100 would be equal to what? So what is that distance? So here, this was 11. and this is 15. What are you over here? So will it be a load here going down? So you have what? Q3 times what? 11, no? That would be a full load. Plus, you could say you could have what? Q2 times S, because it will be the whole length, no? And now this one will be equal to what? Oh, wait, this one I put positive. So minus, sorry, Q3 minus Q1 times what? S minus that distance, no? Minus P72. So if we solve here, you get P72. I haven't do the algebra. No, S minus that distance here from 5 to 7. This is 11 or 15? This is 11. Oh, okay. So you do the whole length, but you remove this one, no? So it will be just like if it's this distance over here. Okay. So we get P72 would be equal to what? Minus 11 Q3, whatever that is, plus, I'm just going to write it, minus Q1S plus 11 Q1 minus 4100. So basically, I didn't do the detailed calculation, but if you do the distribution, you get but positive, negative, really should be positive, but I think, and here I think I got about 1476.9 when I did it. And then here you get something like 0. Okay, so that's basically what I was expecting for the first problem. I think it's kind of similar to what you had on the first assignment. No? Okay. So I think some people go through off because it was here 1500 force at 0.8, okay? And didn't know too much to do with it. And then some people try to overcomplicate it. Someone actually tried to overcomplicate it, but I kind of understood what the person was trying to do. So even though it didn't get the same values, I got most of the points, because as long as your reasoning makes sense to me, is your approach to solve the problem, no? Okay? And if it makes sense, it makes sense. You might get a different answer, but it should not be that off, but you should give something that makes sense. Okay, so let's see problem number 2. I think I had it open and then I close it. All right, so problem number 2. I think basically I kind of gave you the geometry, what you could have. All right, so I'm just going to copy that figure, P2. And let's see, the numbering goes from the left. Okay, so. Okay, and numbering is 1, 2, 3, 4, 5, 6. I'm gonna have to look at one of your exams here. So I can get the data. So I'm not gonna rewrite the data, just follow from the problem. And I think I forgot to put this, but we say that the load V will go from 0.2 from this line. Okay, I think that's something that almost everybody got right, because B1 was equal to B6. So B1, B2, B3, B4, B5, B6, but they were all equal to the same. So basically, we could say that the CG was located where? Right in the middle, no? Okay, so then you calculate the moment of inertia. Most of you got it right. This is X, okay? This is X, let's say this is Y. The bending was about X. And here I just want to make, because somebody did something, but let's put it this way. What is really IXX? Should be equal to the summation from, let's say, R equal to 1 to 6 of what? Of 1/12 of the distance, let's say S sub R, B sub R cubed, plus the B sub R using the parallax theorem. We move this one where? We move this one. This is like AD squared. We move this one to the CG, no? Yeah? But something that I did not say, but we were doing, we said this was equal to what? What happened if we do the assumption of thin structures? What will be this value here? It will be extremely small, no? So we kind of neglect this one. I don't know if I clarify that on the notes. So you could approximate the moment of inertia by just being equal to the summation of the areas times distance to the centroid or the neutral axis squared, no? Yeah, but the simplification comes because of the thin structures. And if you do this, you get 15 inches to the 4th. Okay, so after that, now we make the cut. So step 1, make cuts. So how many cells do we have? We have 2 cells, so you need to make 1 cut per cell. Okay, so I think the easiest thing to do was to make the cuts over here. 1, 2, 3, 4, 5, 6. And then using the equation, so basically we know Q 1, 2 equal Q2, 3 equal to 0. And then we have what? Q 3, 4 will be equal to what? Q2, 3 minus dy over IXX D3 Y4. Sorry. Thank you. So let me run here my MATLAB code, even though I think most of you did that correct. Let me just run it to see what I get. Oh, I run it here. So 15, 5. So you get here 3, 4 is equal to minus 100 over 3, which was minus 33.333. Okay. Now, just you can do the calculations, but even if you want, you can check your calculation by understanding. This one should be equal to what? Q34 minus Vy Ixx times what? So this should be Y3 here. B4 Y4. Even without looking at it, what should that be equal to by symmetry? Equal to 0. Okay? But even, you know, there's also a reason why I made the cuts over here. Mathematically, you can do them anywhere you want. But what is the concept we use initially? Is that only the members in the direction of the force will be resisting the load. No? So in this case, in what direction is the force going? On the Y. So the only members carrying some load should be what? 3, 4, 2, 5, and 1, 6, no? Yes? Okay, did that make sense? So how much was Vy in our problem, actually? I don't remember. But... Okay, so we get this. Then we keep going over here, Q56. So I'm not going to give the details. I just give the value. Q56, we also know it needs to be equal to 0. Q61 gives you equal to 33.333. And Q25 should be equal to what? I mean, I'm going to write this one, but you don't need this. So Q12 plus Q23 minus Vy over Ixx V2Y2, no? Yeah? And this one, again, will also be equal to negative 33.333. We have 3, 4. So 1, 2, 3 should not be 0. 1, 2, 1, 3. Okay? The 3 vertical ones. Okay. I mean, almost everybody followed the step correctly. So step 2 is define the Q bars, no? So basically, let's say Q bar 1, 2. Here we need to define one thing as well. So let's redo a figure. Nothing wrong with redoing figures. Okay, so I probably did this. I don't know which one is which. I'm gonna have to find out on my solution. So let's see, QB12 is Q2. So probably this is Q1. And this is Q2 on my solution. Okay, so Q12 will be equal to what? Q12 plus Q2. I go through this one first. Q56. Let me first do that one. Q56 plus Q2. Q bar 61 is Q61 plus Q2. Then let's do the other one. Q bar 23. Q23 plus Q1. Q bar 34 is Q34 plus Q1. Generally, I don't like to do this, but I want to move it to another page. Q bar 45 is Q45 plus Q1. And now the difficult one is Q bar 25 will be equal to what? Q1 minus Q2 plus Q25. Yes? Okay, look at the figure. Everything needs to come from the figure. All right? All right, so now comes step 3. I would like to see if you change the order, it doesn't matter. External equal to internal. So in this problem, maybe it was a smarter way, but the way when I program it, I took all the moments about the center over here. probably was some smarter one. If you take between 2 or 5, you remove a bunch of them, no? Okay. Okay, so this was this. So basically, if you were doing this, what would be the moment created by the external forces? 0, no? And then the moment due by the internal forces was equal to what? So let's say you will have, I'm just going to try to combine everything, but let's say Q23, so Q bar 23, Q bar 45, Q bar 56, plus Q bar 12. They all have the same distance, no? S whatever, S12, no? That was the same distance as this one, no? S12 is equal to S23, and this is equal to S45 and S56. Yeah, okay. So this is the value of the force, and what would be the arm? Let's say this is H, which is S25 divided by 2. So this will give you the moment created by all these forces. Then what do you need to add? Plus 2A Q bar 34 plus 2A bar Q bar 61. What should be A for both cases? Is the same on the other side, no? Yeah. So A should be equal to what? Pi r squared divided by 2 for half the circle plus what? S23 times S25 is half of the rectangle, no? Yeah, if you look at it, it's half on top, half at the bottom, no? Also, it should be a full one. No, because it's fine, that's correct. Okay, so obviously, I'm not going to do a substitution. I should have here the calculation. I think if you do this, good. Okay, let me see if I can get it a better view. VPA Q1. So if you do this, I think I got that this will give you minus 278.539 Q1 minus 278.539 Q2 equal to 0. So basically, you will get in what over here, Q1 equal to negative Q2. Okay, step 4. So here, this problem we stop over here. The problem was statically determinated. But since it's statically indeterminated, you need to get an extra equation. And generally, the extra equation, you will get it from something that happened on the geometry. So what is the case that happened on the geometry is that we say that the angle of twist of, let's say, the first cell will be equal to the angle of twist of the second cell. Okay? So basically, we are over here where d theta dz, I think, is equal to 1 over 2a integral of, I think I'll give you the equation. I think I should know it by now, but let me double check. Yeah, Q over GT ds. Okay, so I may not give all the calculations, but most of them, and one, two, three, 4, 5, 6. And I think we said this is here Q1. And this is here Q2. Okay, so I think some of you just had a problem over here. And maybe it's my fault because I think every time I was doing in MATLAB, I wasn't able to show a figure. But I think here you needed to stop and do a figure if you did in order to make it right. So let's look at the results we had from before. So if I go back up, let's say to the first page, what is Q12? 0, okay? We have Q23, 0. I'm looking at this page over here, the one we had before. What is Q34? It's negative, and it goes in that direction, and it's 33.333. Okay? Q45 is 0. This is 0, and Q61 we found to be positive, going in that direction here. 33.333. So, okay, so let's say we do d theta. This is 1. This should be equal to what? 1 over 2 A1. What is A1? Should be all this area over here, no? Of the whole cell, okay? And G is the same material for all of them, so we can put the G over here. And the thickness is also the same for all of them, no? Yeah? So basically, only we need to integrate this. So here we need to be careful because, okay, and consider the angle of twist positive going also counterclockwise. You need to select. Okay, so Q23, between Q and 23, there's only Q1, no? Yeah, so we'll be here Q1 times, okay, let's do S23. Let's start over there. Then what about 3, 4? Is that one creating a positive, or is it going clockwise or counterclockwise angle of twist? This is going to make the cell to go clockwise, no? So this will should be positive or negative on this one. So minus 33.S34. But what about Q1 in that section? Plus Q1 S34, no? Because that will be positive. Now, what about 4, 5? So 4, 5 will only be Q1 S 4, 5. And what's going to happen here now between 2 and 5? Oh, what was 2, 5? I didn't put it. 2, 5 was equal to minus 33. So really, this was going up. So now what about this one? Between the 2, 5, what are you going to have over here? 2, 5, you're going to have the Q1 will be doing a positive, correct? The Q25, which is the 33.33, will also be doing a positive. But what about Q2? Q2 will be against, no? Okay, and basically we do the same thing for the other one. You can probably do it on your own. You will get over here 1 over 2A2 GT. Okay, so let's start by the 5, 6. 5, 6 will give you what? Q2 S56. What about the 6-1? This one, let me maybe factor out. You have what? The 33.33 plus the Q2. Both will be positive S61, no? Yeah. Then S12 will be just what? Q2 S12. And now here at the 2,5, what are we going to have? Q2 will be positive. Okay. S25 if you want. S25 will give you a negative. So Q25, which is the 33.33. S25 will give you that way. And Q1 will also be negative, no? Minus Q1 times S25. So now if you equate these two equations, I'm going to do my VPA equation 2. Okay, I get some very, very, very small values. I'm going to change it a little bit, but let's see. 10,000, I'm going to try this by 10,000 matter. Okay, so let's say this will give you, so now you do d theta dz1 equal d theta dz2. And this should give you 0.01282 Q1 minus 0.00928 Q bar 2 plus 0.008825 equal to 0. Okay, so some of you got something different. You did everything perfect, except the procedure was a bit different. So I didn't take many points off, maybe 4 or 5. I mean, not. But if I do that, I get my, let's see. When I'm doing this, so when I substitute this one over here, so solving, let's say 1 and 2, to follow the procedure. I got that Q1 equal to negative 0.3879. So Q2 was equal to 0.3879. Okay, so now next, what do we do at the end? Last step is substitute back into these equations to find the final distribution, no? So step 1, 2, so 1, 2, 3, 4, 5. Final shear distribution. Okay, so if we do the figure, So let's see what I got over here is. I have complicated values. Just rerun all this stuff. Okay. No, I have good values. Okay. So Q12 will be 0.3879, 34. Oops. So wait, 23. This will be negative. This will be positive 0.3879. Sorry, Q12, Q23. Q34 will be equal to minus 33.7212. 45 will be the same as this one here, minus 0.3879. 56 will be positive 0.3879. 61 should be equal to the same as this one, but positive 33.7212. And 25 minus 34.109. Okay, so if you got all the steps correct, and you found that Q1 equal to minus Q2, and then you have different values than this one, you probably got between, I mean, you probably got minimum 9 points out of 10, but I think most of you, I give you 9.5 out of 10. Okay. So any comment about the exam? Yes.
Comparing it to the top one you had used
on this page or another page?
The
First page.
Yeah, that.
This one here?
Nope. The third one down.
So not this page.
Oh, that one comparing the two.
Wait. So I mean, tell me which page. And this one? No, this one is the other problem.
That one.
So this is the first problem.
Yeah. The first problem compared to the current case. So that one you had the Q's pointing towards opposite corners. For problem one, for problem two, you have Q's in the continuous circle.
Correct.
When would it work if we use the circular Q's for that problem? Or like when do we
if you use circular, it can work, but you need to be very careful, and it's not a good thing because it shows a conceptual error. So it's a good question. So let's put it this way. It's a very good question because that's important. We haven't still covered torsion, but it's important to understand the difference. So basically, when you have a structure, just going to make a simple structure this way, that is subjected to a shear force. Correct? Okay. So in that case, you need to say that the convention of the shear will be either this one or the one that will be this one over here, okay? Yeah. And the reason of this is what? It's because this is just a force due to bending, if you want. Okay, to see if you know the difference. So in order for this to be in equilibrium, to be able to use summation of force equal to 0, you need to be able to do this, no? Everything will be 0. Okay. Now, if you have the same structure, let's say now subjected to a torque, okay? So in this case, if you want, the equation will be Q, for the simple case, will be V over I dr y sub r, no? If you want to remember this from structures 1, this is equal to what? VQ, Q, this is Q over here, no? Over I, all right? Now, for torsion, what is the shear flow produced by the torsion? Is TR divided by GJ. This is generally the shear, due to torsion. So in that case, and the shear flow due to torsion would be the same thing, but basically we find another one divided by T. But now, when you have this one, what should be the convention for the shear? You can either use, I mean, Johnny would be the other one, but in this case that you see is that the shear due to torsion will be counter-reacted by a continuous shear, no? And not by this one. Does that make sense or no? And that's very important because the next session we're going to do, that's exactly what's going to happen to each one of the panels, is that if the force is due to shear, you will use this sign convention for shear, but if there is torque, then it will be a continuous one.
So the second problem,
You need to use the best. Correct. Yeah, it's a very good question. So the first part of the problem was what? First part of the problem, we had all this problem over here. Okay. Oops. I mean, these ones were not over here, no, but it doesn't matter. This was subjected to what? Shear. Okay. Now, the second time, and that's where we make the two cuts. All right. Now, the second time, when you use the angle of twist, the angle of twist is due to what? Basically, now what we are saying about the second one, by doing this, maybe I should have mentioned that, is that we are assuming that there is a torque being applied. And that's why in this case is continuous. Okay, the angle of twist will be due to the torque, not to the shear. No. This force over here, what type of motion is the V going to create on the wing or the beam? Just bending, which will be up and down, no? All right. So this should not induce any torsion. All right. However, we know that because of breaking this, when you use the angle of twist, basically what you're assuming is that if you want, there should be some equivalent torque, okay, that will be producing these shear flows. And because they are due to torsion, they will be continuous. Does that answer your question? Okay. But it's a good question because a very good question. Anyone else? No? Okay. Okay, so we're going to continue that problem, but this time for case one. So let me do a quick figure of recalling the problem. So example, continuation. Okay, so let's go very quick. We had this panel over here. Okay, so it was the singles panel, the wing panel can have two flanges and one panel. And basically, I think was at the cut AA over here. We had a force here of F equal 20 kilonewtons applied. This was 200. Cut one was at 1,000. Cut two, the whole length is 2,000. And then this height over here was 400. Okay, but this time, let's solve it considering case one. So considering case one, which is what? Again, no effective in resisting bending. So in this case, it's like to substitute into that long equation. Remember, we have V over I, open parentheses, could be equal to the B sub R, Y sub R plus the integral of the TDS. Okay, I mean, I don't have it here in front of me. So the T is equal to 0. So following the procedure we have for case 1. So following the procedure is we say in that case that the load PC1 was equal to mx over h. PC2 was equal to mx over h. So once again, remember we say, I don't like to put signs, I'd rather have the explanation. If the load is going down, the top of the spar is going to be in tension or compression? Tension, and this is spar 1, spar 2, and this one will be compression. Okay, so at the cut, this is very simple, but we did that before. What did we have before? In this case, what should be the height over here? This should be 300, no? So at the cut, what should be? At the cut, we say that this height over here is 300. And what is the moment? What should be the moment? 20 kilonewton times 1,000. So this is millimeters. So this will give you M will be equal to 10, 20, 10 to the 6 newtons per millimeter. Okay, so if I substitute into this equation, we get PC1 will be equal, whatever, to 20, 10 to the 6, divided by H, which will be 300. PC2, 10, 20 to the 6, divided by 300. And this gives you 66,666.67 newtons and negative 60. Oh, I mean, don't put negative. Okay, it doesn't matter. I put the negative now. Too late. 666.67 newtons. Basically, the negative means that this will be in compression. Okay, and remember once again that in this case, you have the P1 out of this flange is going down. So this is your PY1, this is your PZ1, and in this case, on this one was going up. So this is your P2, PZ2, PY2. Okay, from geometry, you can go back to your notes. Py1 we say will be equal to what? Pz1 tangent alpha 1, where this could be alpha 1, this could be alpha 2, or we could say this will be Pz1 delta y sub 1 over delta z sub 1, and Py2 equal to Pz2 tangent alpha 2 or Pz2 alpha delta 2 over delta Z2. So if you remember, what about you go back and remember how did we do this? This is the change in height with respect to the length, no? Basically, you can say the slope of this flange or stiffener, okay? So basically for this case, we say it could be equal to what? 200. Now if we take from here to here, no? 200 divided by 1,000. Yes, or we could do from here to the end. Go back to the previous lecture. Remember, it's the change in height of this curve here. And we calculated to be this equal to, having here is 120 for both cases, okay? So if you do these calculations, you get for this one, 3,333.3. And since we're keeping the negative value, but I don't like to put the negative value, but since I put it, let's just keep it over here. To have this. Okay, and that's the reason why I don't like to put the values is because of the next step. I think we did that 2 lectures ago. We do all this stuff to find the shear in the panel is. And basically you do that I might do a bad figure, but at least would be more significant than the other ones. Basically, what do we have over here? We have I do it up or down. It can go up or down. Just do a general case. Do you have the notes from the other day to see how I plotted this one to do the same thing? I'm gonna have them here. So our last lecture was 10. So you see that's the example we did. Basically, all this stuff is kind of similar, but we found the IXX, IYY.
Are you trying to error number screens?
I'm moving now. Okay, sorry. I'm moving now to this side. Yes, basically that's what we did last time. I mean, before the exam, we started this problem, but we started with case 2, no? Okay. So basically we went through the whole thing for the case 2. So we find the PZ1, PY2, and then probably I said the same thing. You see here, this is the tangent. We said it would be equal to 200 minus this 100 divided by the whole length, which should be the 200 minus the 150 divided by the 1,000, and was the 120, no? Okay, so it's good. We have here, we substituted, we have different values. You see, that's what I don't like. This is the figure I wanted to show, okay? So you see, we make this one going down, so let's make the same figure. Let's call this one the external, the internal, okay? Let's do the same figure, that way we can match, okay? So let's do here. The external, put it the other way around, put it down. And then the other one will all be going up, so it should be here. I call this one V panel. I guess this one will be PY1. And this one here should be PY2. Okay, basically this is, oh, I did it going down. All right, so no, that's the one I'm using now, so don't use that one. Okay, doesn't matter. I don't have to open one. What happens? So all and reopen here. All right, let's go keep going with this one and then I can go and look the values. So basically, what is the idea over here is that summation of external forces needs to be equal to the summation of internal forces. So let me find out what I did on the previous one. I need to know, so lecture 10. It was last page of lecture 10. We're going to do exactly the same thing over here. Now we're going to say that those 20 kilonewtons will be resisted by this one, no? Okay, going up. So we can put 20 kilonewtons. So the 20 kilonewtons here should be resisted by the PY1 plus the V panel plus the PY2. So from here, I'm just going to look here at the magnitude. So the V panel will be equal to the 20 kilonewtons minus PY1 minus PY2. So V panel is really equal to 20 kilonewtons minus, what do we have? 3,333.33. That's why I don't like here. Then what should be this one? We are just looking at the magnitudes, no? Minus 3,333.33. And that should give us, maybe I can move now, over here. This from the other day, so that's not the one I want. I mean, you can do a calculation if you want, so that way I don't have to look at it. It should be a quick calculation. Go. So that should give you here 13,000. $333.34 newtons. Okay, to tell you the truth, guys, on both examples, the last one and this one and the last one, to be perfectly correct, what should I have put if I did this plot? I should have put here what? Negative 20, no? Okay, and then, but let's put it this way. So this should really be negative, but it's fine. Let's give it this way, okay? Let's just get about the magnitude. So VB would be 13.533. Okay, so for case one, it is known what? For case one, what was given to us is to say that QS will be approximated, which is by what is not done most of the time. Generally, the shear is approximated by what? The force going through the cross section divided by the depth, no? Yeah, that's the simplest approximation you can do. So in this case, what is the value of the shear going through the panel? Is a 13,333.34. What is the depth of the panel at the cut AA? We say was 300. So this gives you over here 44.45 newtons per millimeter. So what's important here to notice is that if we plot this, in this case, what are you gonna have? This should be a straight line. Sorry, guys, should be a straight line. $44.45. So this is case one. And what is the stuff that we got before? On case two, I want you to see the difference. What do we have on case 2? We had here a constant value, but then we have a maximum value over here. Here we had 39.14. Here we had 53.8. So what's important here to realize is that you need to be aware that if you use case 1, you're just gonna find what? An average value of the shear. So if you multiply the 44.45 probably by the height, whatever value it is, will probably give you a value that is very close if you integrate the whole area of this one, no? But what you need to be careful is that this one will give you an average value. This one will give you a maximum value, no? And if your design is to be very accurate, what is the difference between this value and this value is actually 17%. So in this case, it's not that much, but it can be crucial in your analysis, no? If you try to make it without a safety factor that is reasonable. Yeah. Okay, I know it's time.